I'm going to explain techniques for drawing a derivative on its graph. So this is really graphical. We're not basing this on finding derivatives of functions or differentiating functions. So we'll start here. The idea is we've got a quadratic function. It's polynomial basically. It's differentiable, smooth everywhere. And I attached a tangent line to it, and I'm going to move this point. And as I move the point, we have the tangent line. And whatever the tangent line's slope is, I'm going to plot that point. So I take the x value of where this point is, and the y value is the slope of this tangent line, which is the derivative. I'm going to plot that. Right now, it's very high because it's a steep line, so it's not in the screen. You'll see that as this tangent line begins to flatten out, as we reach this local maximum, it's going to flatten out. You see now we have the derivative being graphed. So again, the y value of this point is the slope of the tangent line. So this is graphing the derivative. Speed this up a little bit. So what you'll see is that I'm increasing, so my derivative is positive. As I go through this local maximum, I should have a flat tangent line, so therefore my derivative should be 0. The colors here don't signify anything, just thought they looked nice. So it's flat, goes through 0. Now I'm decreasing, and so you see my derivative is negative. Now I'll be at my steepest point going down right about there, and then that's going to be a point of inflection. We'll talk about that later. But the idea is that right in here, I'm going down at the steepest I'm going to be going, and so my derivative should be at its minimum. So I'll have a minimum in my derivative at this point of inflection of my function. And so as I pass that point, I'm still decreasing, but I'm not decreasing as fast. So my derivative is still negative, but it is not as negative. So speed this up a little more. So again, as I pass through a local minimum, my derivative will be 0. And right there, I'm also starting to increase, and therefore my derivative is positive. And so we'll get one more local max here. So increasing, increasing. When I'm increasing my fastest, that's when my derivative will be at its greatest. So that's my point of inflection, corresponds with the maximum of my derivative. And when I hit my local max, my tangent line's flat, so my derivative is 0. And there we are. And you can see that it's graphing out a cubic function, which makes sense because the derivative of a quadratic is a cubic. Okay, this is non-differentiable. Here we have an absolute value function. If I graph the derivative, constant slope, there it is. Right at the kink, it's not differentiable. So when you graph the derivative, you should put open circles there. So right there, the fact that they correspond there is coincidental. See, then it flips up and suddenly it's increasing but constant. Now here's a cusp. So if we move the point here, we're decreasing, and we're decreasing faster and faster and faster. And as we get towards this cusp, it's continuous but not differentiable. At this point, we're going down infinitely fast, and our derivative drops off. And we come out of it infinitely fast. You'll see our derivative is up here because we were increasing infinitely fast, and we're approaching being flat, and so our derivative approaches 0. Here's a vertical asymptote. And so the left side will look pretty similar. Here I'm decreasing a little, so I'm a little bit below 0. I'll decrease faster and faster. My derivative is more and more negative. Here I'm also decreasing very, very fast. You'll see when I come out of this asymptote, my derivative will be negative because I'm going down very fast. When you start looking for symmetry, it gets confusing. It's better just to think of derivatives as slopes. And here I'm approaching flat, but I'm not reaching it. So I'm approaching 0 for my derivative, but I'm not reaching it. And here we have a horizontal asymptote. Again, here's I have a local min. So my derivative will go through 0. I've got a local max. My derivative goes through 0 again. And you see I'm approaching a horizontal asymptote. That's what's in red here. And so my derivative will approach 0 because I'm approaching being flat. Okay, let's do a few now. So here we have a polynomial. So what I would do first when I'm graphing the derivative is I look for these places where I've got flat tangent lines. So local max, local min, local max, And now this is increasing, which means my derivative will be positive. This is decreasing, so my derivative is negative. Now my point of inflection is maybe somewhere in there, and so I'm going to try to have a minimum of my derivative there. Over here my point of inflection is maybe somewhere in here, and so I do that because I've got to connect up these points, of course, and now I'm decreasing, so I have negative derivative, and it's just decreasing faster and faster. And as you see, this looks like a cubic, which is the derivative of a quartic. Okay, different situation. First thing I would do here is I'd put a point there to correspond to this minimum. This looks parabolic, and yet it is going up to an asymptote, so it's not quite. Okay, so we're decreasing, which means we have a negative derivative. And now we're increasing here and increasing faster and faster, approaching this asymptote, so I would probably do that. So it almost looks linear, but you do have to approach the asymptote, so you have to start curving toward it at some point. And over here, I'm increasing very, very fast at the beginning, so my derivative is very positive, it's up here. And then I'm approaching being flat, and so my derivative will approach 0, because if you actually do flatten out, then you do have 0 derivative. Okay, for this one, I have a negative constant slope, about negative, a little more than -2. So what I would do is draw a straight flat line, open circle. Here I have a positive slope of maybe, it's about 3, no, it's 1.5 actually. And so I got open circles on both sides because neither one of these points is differentiable. Here I have a slope of 0, which again is constant, and neither point's differentiable. Positive slope again of about the same one as this because these pieces look parallel. And finally 0 slope. So that's how I would graph this function. One more. Okay, this is 0 here. Here we have a minimum here. It's flat right in about here, but it's not a max or a min. So we're increasing, which means I've got a positive derivative. We are decreasing. Okay, so actually we want this to be smooth, and so we're going to have to connect up here, but we're not going to keep going up. The point is that it's decreasing, so negative derivative, then it's flat, then it continues to decrease. So I'm just going to bounce off. I'm going to bounce off this axis, and then I will come up here, and then I'm increasing faster and faster and faster. And so it would be nice if this point matched up with my point of inflection in about there. But that's the point I'm trying to make, is that just because you have a 0 derivative, it doesn't mean that your original function had a min or a max. As we see here, it's not a min or a max, and in the derivative you can see it bounces off.